minutes for discussion.
Okay.
But we're just waiting because we've got a couple more minutes to go.
Yeah. So I'll just reshare 1 second.
Okay. Okay, good afternoon all, and we're just about to start the second talk in this block of talks, and it will be by Sue Chan, and she's going to speak on bounds on the inducibility of double loop graphs. Thanks, Sue.
Thank you. So everyone can see my screen okay? Yeah, okay. Good afternoon, everyone. I'd like to thank the organizers for the opportunity to present my work. This is joint work with both my supervisors, Kerry Morgan and Yuan. For this talk, I will be explaining the notion of inducibility of graphs and give an overview of the existing results in this area. Then I will demonstrate the main parts of my proof for the bounds on the inducibility of the family of double loop graphs. Okay. All right, just a warm up. We'll do a refresher on the basic graph terminologies. A graph G is a set of vertices and edges connecting pairs of vertices. Now, just to clarify, the order of the graph refers to the number of vertices and the size of the graph refers to the number of edges. And the density of a graph refers to the number of edges over all possible number of edges in the graph. Next thing is a subgraph. A subgraph of G is the subset of vertices and edges. Whereas for a subgraph to be an induced subgraph, we need to include all the edges that are also in G. So as an example to illustrate this, the difference between the subgraph and induced subgraph, look in the figure for graph G. We've got graph G on the left side, and we've got two graphs H and K. H and K are both subgraphs of G. However, only K is an induced subgraph of G. Okay, now that we've got all the basic terminologies, now I'm going to introduce the notion of inducibility. So if we recall from the previous slide that the density of a graph refers to the number of edges in G over the maximum possible number of edges in the graph. Now, here, the induced density refers to the number of subgraphs of H of order K over the maximum possible, all possible K vertex subgraphs in G. The condition here is that N has to be greater than or equal to K. So now the problem of inducibility that was first introduced by Pippinger and Golombek in 1975 asked the question, what is the maximum induced density of H and over all N vertex graphs G? So it's not hard to see that this induced density approaches a limit, and notice that this limit is actually called the inducibility of H. And also this limit falls between 0 and 1. Right, now some facts. The exact inducibility of small order graphs are known, so order of up to about 5, and a handful of graph classes. So for example, the cycles, the complete graphs, and bipartite graphs. As a trivial example for this, we'll look at the inducibility of complete graphs. So if we have a complete graph of order n, all k-vertex subsets of the complete graph will also be a complete subgraph. And this is in the extremal case, so we can see that the inducibility of a complete graph is 1. Now, although we do not have the exact inducibility of all graphs, we do have a lower bound for all k-vertex graphs, and this was first given by Pippinger and Golumbik in their original paper. Right. Here in this table, we give the exact inducibility for graphs of small order, so 3 and 4, and its relevant extremal construction. So referring back to the case where we have the complete graph, the extremal construction for that will also be a complete graph. And I noticed from the table, we have P4 was one of the cases that it's still not been determined up till now. And also, we noticed that we have the exact inducibility for C3 and also C4. But only bounds are known for cycles of higher order. So this brings us to the motivation of the study. The inducibility of cycles is one of the more well-studied problem in this area. The lower bound for this family of graph was first given by Pippinger and Golumbik as well. And if you notice with the lower bound, it is the same for all k-vertex graphs. And in recent years, Crowell and others gave an upper bound for the same family as well. But this bound is not tight. So the natural next step is to look at graphs with sort of similar cyclic properties. And our choice of that is the family of double loop graphs. So what is a double loop graph? A double loop graph LK on k vertices is a graph where the vertices are labeled from 0 to k minus 1, and each vertex I is connected to vertices I plus minus 1 and I plus minus 2 and indices in modulo k. Just an example, in the figure, we've got a double loop graph of order 6. And if we look at V naught, the vertex V naught, it's connected to vertices V1, V2, and also connected to vertices V5 and V4. Similarly, you can see that sort of cyclic property of the double loop graph. For V1, it's connected to V0, V5, and then also V2, V3. Okay, and now that we know what a double loop graph is, we will present the following bound. So we've got the theorem, and for the rest of the talk, we'll be focusing on the proof for the theorem. The lemma follows from the theorem. So now for the remainder of this talk, I will present highlights from our results of the upper bound of the inducibility of this family of graphs. All right, so the main ingredient of this proof involves counting tuples that induce subgraphs that are isomorphic to LK, which is our double loop graph. So if a k tuple induces a double loop graph, we call this tuple a good tuple. And the process of building this set of k tuples, it's conditional. So we pick the first vertex, and then the second vertex is conditional to what we've picked previously. So then if we have a tuple that is less than the length of k, we would call it a good prefix if and only if it has potential to give us a good tuple. So to build around this, we build a probability distribution where we have these necessary sort of conditions. V naught is given, so V0 is the first vertex that you would choose to build your tuple, and it's sort of the number of possible vertices across your whole large graph. V1, because you don't really have a condition, you just need to look at the degrees of your first vertex. The condition for the last vertex is that it has to close the tuple such that it induces a double loop graph. And the choice for VI is where you choose the, it has to be neighbors of VI minus 1 and VI minus 2. That is the condition of the double loop graph. Also, the important part of the proof is that the tuples are ordered. And also, the good thing about this sort of graphs is that we can take advantage of the symmetrical properties of this type of graph. And because for any sort of chosen vertex, you can see around that sort of cyclic symmetry, we'll almost always get the same sort of probability, but it could also depend on the first vertex and the last vertex of your choice. Okay, so to illustrate the idea of this probability distribution, I'll use a small example. Here, we're going to try and find a tuple that induces a double loop graph of order 5. So that's the smallest double loop graph in this family. We start off with a graph on 10 vertices, and to pick the first vertex, we've got 10 choices. So the probability of picking V0 or the first vertex will be 1 over 10. And suppose we pick V0 as our first vertex and it's colored in red, and we start building our tuple, and so we put V0 as our starting vertex. So next we look at the degree of V0, and you can see that there are 8 choices because there's 8 neighbors for V0, and we can pick either of these. So here, and if you look at the vertices colored in blue, you can almost call them, wouldn't say forbidden, but there won't be good choices, because if you did pick any of those vertices, you're very likely to not be able to extend your tuple to get a good tuple. So to illustrate this example, say if I picked V6 as my next vertex, and so now I've built my tuple starting V0, V6. Now then I've got 3 choices to choose my third tuple, so third vertex. Here, remember the condition is that for VI to be chosen, VI has to be also adjacent to VI minus 1 and VI minus 2. So here we've got 3 choices, and say if we pick V2, and then we're trying to pick our fourth vertex, but what we notice is that none of these choices here that are colored in yellow will suit the criteria to be the vertex, the choice for VI, because for V3, V4, and V7, they're not connected to V6. So then we're stuck there. So that will be just a prefix, because we can't extend that any further to give us a good tuple. So then our probability for this prefix here gives us, we multiply all the probabilities together, we get 1 over 240. All right, so we start over, and then we start from V0. So now pick V1 as an obvious choice. And we've got the 5 choices to pick the third vertex. Here, I'll pick an obvious choice, I'll pick V2. And from V2, we've got the green vertices indicate there's 4 choices, but recall that we need to have them connected to VI minus 1 and VI minus 2. So V7, if we see that node over there, it's not connected to V1, so we have to omit that as a choice. So now we've got only 3 choices. And so we pick V3. And lastly, if we look at the last 2 choices to close that tuple, V8 doesn't fall into that criteria, so we can only pick V4 as an obvious choice. So now multiplying that to get the probability of getting that good tuple there, we've got 1 over 1,200. So this is sort of the smallest case for our smallest double loop graph, where we've got a complete graph, but it gets a bit more complex when we have higher orders, because we need to make sure that the vertices are connected to, for the last vertex, it has to be connected to VK minus 2, V0 and V1, and so forth. So the conditions are necessary. Okay, so now the question is, what's the point of this probability distribution? Now let's name the good tuple. We'll give it a name. So say D represents the good K tuple. And then we've got our probability distribution as the product of the probabilities for picking VI. And we use this and we take the probability distribution across all these good tuples to prove the AM-GM inequality to get our bound. I won't go into too much detail about this, but we will be just finalizing our paper, and we should be submitting our paper onto arXiv really soon. And if you're interested, you can have a look at how the proof works. All right. So for the last few parts of the talk, we're going to talk about the results. So we've looked at some upper bounds for small k of the double loop graph. In the case of k is equal to 5, as we've seen from the previous example, for k equals to 5, we get a complete graph. Using our lemma, we get the upper bound, which can be seen that is close to the inducibility of complete graphs. That's a very promising result. And for the case for k is equal to 6, from our upper bound, we get 5/12. And using our method of construction, we obtain a lower bound of 10/81, which gives us a factor of about approximately 3. And so lastly, the current work in progress is we're looking at the case for k is equal to 7. So recall from the previous few slides where we talked about the inducibility of a graph and its complement are the same. So, and the complement of a double loop graph of order 7 is indeed a cycle of order 7. So we know what the lower bound of the cycles is, and we've got the upper bound from our, using our lemma. Now, using the lower bound of cycles, we obtain the following, and these two give us within a factor of 27. So the current work in progress is that we're trying to find a construction that could give us a better bound so we can close the gap a bit further between the two bounds. And yeah, that's it for future work. Since we've looked at graphs with symmetrical properties, we're potentially look into families of graphs with almost symmetrical properties and potentially look at finding a general construction for graphs with some sort of symmetry. They might not be the cyclic symmetry, but they could be sort of a reflexive symmetry. Okay, and that's all for my talk. Thank you for listening.
Okay, thank you, Sue. Are there any questions? Now, I can't see people, so if you can make yourself known if you have a question or put it in the chat, that would be great. No questions?
It looks like no one else is asking, so I'll ask a little bit. So one way to view what you're calling these double loop graphs is as a Cayley graph, where you have, you're thinking about the cyclic group and you have two elements of that being the +1 and the +2, and that generates your double loop graph. How different do you expect it to be if you take two other elements? So if I took +1 and +3 rather than +1 and +2 or whatever, how much do you think will change if you vary those two generating elements? Do you expect the bound to change a lot or be similar?
I think because if we still keep within that sort of same not bound, but the, +1, +3, you're still going to get a 4 regular sort of graph.
Yep.
I would expect it to be quite similar as well. We haven't really looked into it, but that could also be potentially something that could look into in the future as part of future work. Yeah, if we vary that sort of value here, I'll just go up, sorry. This one here, these values 1 and 2, right?
Yes. Yeah.
Yeah.
That's right.
Yeah. I expect it to be quite similar. Would probably have to try work it out and see if we'll get sort of a close-ish bound.
It also strikes me as an interesting question to look at so not just thinking of your small graph as being a Cayley graph, but looking for copies of that in a large Cayley graph. So you could take the graph you're looking for to be generated by some particular values, mod k, and then you could look for copies of that in a larger Cayley graph, which had other generating values. And I mean, there would be a lot of different possibilities there, but there could be some interesting theorems about how many copies you see of the smaller Cayley graph induced in the larger one. Have you thought about that at all?
No, that's a very interesting point. So smaller Cayley graphs and larger ones.
Yeah, well, I mean, you're trying to find. I mean, you've got 2 directions that you want to find bounds for. One is that you want to actually show that you can achieve a certain density of these things, and the other is to show that you can't achieve a much greater density. But but in terms of constructions, it seems plausible that you could get some nice value out of thinking about how many copies of a small Cayley graph you get as induced copies in a larger Cayley graph, depending on what set of generators you use for the larger Cayley graph and so on.
Okay.
I mean, it could get into some quite difficult number theory and so on, but I think there might be some quite nice constructions there.
Yeah, I'll have a look into that. Thank you.
But anyway, nice talk. Thank you.
Thank you.
Thank you for your questions, Ian. Does anybody else have any questions? So Sue, do you have an example, say, of a graph that doesn't have that cyclic symmetry, the types of graphs that don't have full cyclic symmetry that may be a natural next step? So I think you had a suggestion on your final slide or something?
Yeah. Sorry, need to stop moving on. So maybe I'll just bring up that, like almost symmetrical.
Yeah, or with some symmetry.
Some symmetry.
Families were you thinking of there?
So graphs, maybe similar graphs, but with 1 or 2 sort of edges missing, that type of graphs. What other graphs would be? I don't think of anything on top of my head at the moment.
That's okay. So if there's no more questions, well, thanks, Sue, again. You can either clap with your emoji or clap like this. It doesn't sound very loud. There you are. And we will have a 5-minute gap before the next presentation anyway. So just to allow any changeovers. So thank you, Sue.
Thank you.